So welcome to the first lecture on acid-base equilibrium, and this is going to be very, very important for the lecture that is talking about acids and bases and titrations and buffers, which is what the exam number 2 of this semester is all about. So it's very important that you get a good solid foundation on acid-base equilibrium. The first thing you want to discuss is talking about the H plus ion in water. And when you learned about the ions, we learned that H plus was the hydrogen ion, but in reality, H plus ion is a proton and does not really exist in nature. Okay, it's unstable, and by itself, it's going to want to bond with something else. And so really what's happening is that the H plus ion is really the same thing as the hydronium ion. So when you talk about what acids do in water, you may have learned in the past that if you have something like HCl, which is a strong acid, and when you put it in water, in the past you would have learned that it would have been something like H plus AQ and Cl minus AQ. And that's one shortcut of how we can represent it, and it's perfectly acceptable to do that on the AP exam for acid. But a better representation of what's actually happening when an acid is in water is that you show it's reacting with the water molecule, and the H is going to give up, HCl going to give up its H plus ion to become Cl minus, and the H plus will go over here to become H3O positive. So a solution of a strong acid, for example, or any acid for that matter, is really consisting of a lot of the anion of that acid and lots of hydronium ion, H3O plus. Okay, so you want to make sure that we clarify this. And by the way, we call this process of reacting with water, you know the term here, it is called hydrolysis. Okay, so when I say that an acid or a base undergo hydrolysis, we're talking about its reaction with water. So a major theory is called the Bronsted-Lowry theory, and the Bronsted-Lowry acid is a species that donates H plus or H3O plus ion, and bases accept H plus ion. And you can really only identify a Bronsted-Lowry acid and base in the context of an overall reaction. So let's take a look at this example right here. Okay. You need to look at the left side and compare what is happening on the right side. And HA just represents some generic acid. Okay, so when we see what's happening, we can see that the HA is donating its hydrogen over to the H2O to become H3O positive. So in this case, HA would be known as the Bronsted-Lowry acid because it's donating a hydrogen. So I'm going to use the abbreviation Bronsted-Lowry BL acid. And normally we think of water as being neutral, but in acid-base theory, Bronsted-Lowry theory, we can think of whether water is gaining a hydrogen or whether it's losing a hydrogen. So in this case, comparison with the right side, you can see that the water must have accepted the hydrogen from HA. So that makes that a Bronsted-Lowry base. Okay. Which brings us to the terminology what a conjugate acid and base pair is. So when an acid gives up a hydrogen, what is left over is the conjugate base. So in this case, a negative is going to be known as the conjugate base. And for H2O, which is acting like a base in this case by the Bronsted-Lowry definition, when it gains a hydrogen, it becomes H3O plus, which is a conjugate acid in this case. So a conjugate acid base pair is really the same thing as conjugate base acid pair as well. So we can say that HA and A negative is an example of a conjugate acid base pair, as well as H2O and H3O positive. Okay, I'm also going to take a moment here to talk about writing a hydrolysis equation for bases. So I'm going to use a species. I'm just going to call in this case B negative as a generic base. Okay, I'm going to say aqueous. And let's say that base reacts with water. Okay, so the base is going to, I'm going to say it's a weak base. So it's going to accept a hydrogen from H2O to become HB, aqueous, and that H, when that leaves H2O, can leave behind an OH minus, aqueous. Okay, so let's see what's happening in this case. Okay, this time the hydrogen is going from here to here, evidenced by the fact that you have HB on the right side. So this is now the Bronsted-Lowry base, whereas since this is giving up an acid, this is the Bronsted-Lowry acid. B negative becomes HB, so that makes that the conjugate acid, and OH minus is what's left over after Bl, H2O, Bl acid, gave up its hydrogen, so that becomes the conjugate acid. So in this case right here, the conjugate acid base pair would be B negative and HB, as well as H2O and OH minus. And please note that would be a hydrolysis equation for a base as it's reacting with water. Okay, please make this note of this correction here to your lecture notes, conjugate base specifically. So a very strong acid, the weaker conjugate base would be. Okay, and let's just make sure you understand why that's the case. If you have HF, which is a weak acid, and it reacts with water, that undergoes equilibrium to become F negative, aqueous plus H3O positive. And then we're going to compare that to, say, something like HCl, which is a strong acid. I'm only going to write it just one reaction, H plus and Cl minus, just to save ourselves some time. Okay. So if you think about it this way, this is a weak acid right here. And then this one is a strong acid. And you're going to want to note that because HF is going to be really weak, that means that you're going to have loss and loss and loss of HF in a teeny bit of F negative and H3O plus. Okay, for a strong acid, you're going to have loss and loss of the H plus and Cl minus, but only a tiny bit of HCl, because that's what the definition of a strong acid is. It favors ionization, whereas a weak acid does not favor ionization so much. Okay, and so that ties us into what we're talking about here. Weak acid only partially dissociates in solution and exists as a mixture of molecules and ions, which is what I was talking about right here. Okay, you have all of these molecules and ion as well right here. These are the ion, and that's the molecule. Okay, so because HF is weak, it's going to favor this side, which means F negative is conjugate base is not going to be very strong at all. So the way to look at it here is that HF is really weak, which means it's not going to have any F negative, and that F negative is going to be much more willing to gain a hydrogen from H3O plus to become HF. Okay, which means that F negative will be, relatively strong, whereas the Cl minus right here is not going to want to, as a base, is not going to want to gain any of this extra H plus. So that Cl minus is going to be extremely weak compared to the F negative, which is likelier to want to gain that hydrogen. Okay, so in terms of the overall strength, the F negative as a conjugate base is going to be stronger than the Cl minus conjugate base because it is more willing to gain a hydrogen to become the conjugate acid. Okay, note that's a little bit confusing here, but you really want to make sure you understand that because that's going to be important for the rest of this unit as well as the next unit. Okay. Now, this is very important to note. Okay, a strong acid has a negligible conjugate base, meaning in this case that it is extremely weak. Okay, and basically has very low impact on the pH. Okay, so an example would be HCl. It's a strong acid and its conjugate base, Cl minus, is negligible. Okay, a weak acid such as HF, its conjugate base will be F negative, and that conjugate base is weak, but it still has an impact on the pH. Still impacts the pH, so make sure you note that. Okay, and a negligible acid would have a very strong conjugate base. And maybe one I could think of would be like CH4. Okay. And when that one undergoes hydrolysis, it is acting as an acid. Okay, and then this water is acting as a base. Okay, then this is going to become CH3 minus and H3O positive. This is going to be the conjugate base, and then this is the conjugate acid. And CH4 is really a negligible acid, which means that CH3 is going to be an extremely strong conjugate base that will have an impact on the pH. Okay, so make sure you take a moment to wrap your head around what all of this negligible acid and conjugate base would be, the strength of the acid-base combination. Okay, now, next thing here is in every acid-base reaction, the position of the equilibrium favors the transfer of a proton away from the stronger acid. So let's think about the reaction of, say, for example, HCl. I'll write this one out here, aqueous, and let's say it's reacting with the conjugate base F minus. And HCl is going to want to give up a hydrogen. Okay, assuming it's acting like a Bronsted-Lowry acid-base reaction, and F negative is going to gain a hydrogen to become HF aqueous. Okay, so we know that HCl is strong acid, whereas HF is a weak acid. Okay, so since HCl is a stronger acid, that means ionization is favored, which means that the Cl minus ion is going to be more predominant over the F negative ion. So in this case, the equilibrium is going to favor the products. So products favored. And because in this case the products are favored, that means the equilibrium constant of this reaction will be greater than 1. Okay, so people think that because the HCl is a stronger acid, it's going to favor the side of that strong acid, but it's really reality it's the opposite, as it's going to want to favor the ionization of whichever acid is stronger. Good. Now, water is very interesting. We don't think of water as being an electrolyte, but it is. That's why you're not supposed to be in, say, water when you have the middle of a lightning storm, because water can conduct electricity, although not nearly as well as, say, something like salt water, where the electrolyte can conduct the current really easily. Okay, so this is the equation for the ionization of water, which shows that the H2O, two water molecules, are going to ionize to form a hydronium ion and a hydroxide ion. And that's a very big equilibrium because that shows how water is neutral because it's got a balance of H3O plus and OH minus ion. So Kw is the ion product constant that is associated with that equilibrium that we just talked about. And it's very important to note that at 25 degrees Celsius specifically, the ion product constant of water is 1 times 10 to the negative 14th. Okay, and let me go ahead and rewrite that equilibrium right here. H2O gives you H3O plus and OH minus. Okay, and the value of Kw is much smaller than 1. So that means that reactants are favored, heavily favored actually in this case. Which means that there's not much H3O plus ions and not much OH minus ion. Okay, now at equilibrium, right, pretty much any case for water, H3O plus concentration equals OH minus concentration for water, specifically. Okay, at 25 degrees Celsius and only at 25 degrees Celsius, H3O plus concentration equals 1 times 10 to the negative 7th molar, and OH minus equals 1 times 10 to the negative 7th molar. Okay. And this means that the pH of water equals 7, but again, only at 25 degrees Celsius. Okay, at different temperatures, the dissociation of water does have a different K value, and you'll have to learn, using your thinking skills, whether the process is endothermic and exothermic based on the pH of water at different temperatures. Okay, this leads us into the last part of the lecture, which is being able to calculate pH. And you've learned in earlier classes, maybe in middle school, as to what pH means. And you've learned maybe in earlier class that pH less than 7 indicates acidic, and a pH greater than 7 is basic, and a pH of 7 is neutral. Okay, then the main calculation that you have to deal with is that the pH equals the negative log of the hydrogen concentration. Okay. So regarding sig figs, the rules are a little bit weird about this one, but the number of sig figs in the starting number is equal to the number of sig figs behind the decimal after you take the log. Okay, so in the example of this one, if the hydrogen concentration equals 0.10, I'm going to make that molar. Okay, you notice that this number is 2 sig figs. So you take the negative log of that, and that equals 1. But because you have 2 sig figs, that means you need to have 2 decimal places after the decimal to indicate the fact that you have 2 sig figs. Okay, so that's the general rule for how to do significant figures when logarithm is involved. And I don't think that the AP test or the College Board really emphasized it as much as they used to, but it's still important for you to know that. Okay, another scale, not as common, but we can use it to help us facilitate our calculations, is the POH scale, and that's used to measure the hydroxide concentration. So POH means negative log of the hydroxide concentration. And probably should have noted this earlier, but the P means that you take the negative log of something. So if you see something like later on, if you see pKa, that means you take the negative log of the Ka value or PKSP, would be the negative log of the KSP value. And we do this to help us with dealing with numbers that are not in scientific notation, because that can be easier when it comes to measuring something instead of saying 1 times 10 to the negative 14th or 10 to the negative 12th or whatever. So the relationship between the pH and the POH scale is that if you add the pH plus the POH, it equals 14. Okay, so let's go ahead and apply some of these calculations. Okay. Now I want you to know that these are strong acid and strong bases. So HCl is a strong acid. And you learned from the summertime that NaOH is the strong base, and calcium hydroxide is also a strong base. So you have to determine the pH of a 0.005 molar solution of HCl. Okay, you should know earlier that the strong acid is going to completely dissociate into H plus ion and Cl minus ion. So if the pH, if the concentration of this HCl is 0.005 molar, that means after ionization is complete, the concentration of both of these will be 0.005. Okay, so since the H plus is 0.005, the pH of that HCl solution is negative log of 0.005. And go ahead and take a moment in your calculator to say that is 2.301. However, because it is only one sig fig in that problem, you only have one place behind the decimal, so we're going to say a pH of 2.3. Okay, for the second one, NaOH is a strong base, so its hydroxide concentration equals the concentration of the base itself. So we're going to first find out what the POH is. So negative log 0.02. And then we put that in the calculator. And we get 1.699. But in terms of just one sig fig, that's one decimal place. So that becomes 1.7. But the question specifically asks you for the pH. So we say 14 minus 1.7, which comes out to 12.3. Okay. Now the next problem, the hydroxide concentration is actually going to be, because it's for every CaOH2, you're going to have two hydroxide ions. So the hydroxide concentration itself is going to be 2 times 10 to the negative 5th. And we're going to go ahead and use that to find the POH, okay, which in this case would be 4.7. The negative log of hydroxide comes out to 4.7. Therefore, the pH of that will be 14 minus 4.7, which is 9.3. Okay, so remember, you can only do the calculation for a strong acid and a strong base, but when it's a weak acid and a weak base, then you need to do some further calculations involving Ka at equilibrium, which we're going to do in the next lecture. Okay, so that's it for the basic part of understanding acids and bases.